So now we have to discuss the electric field inside a uniformly charged spherical shell. Now this is a spherical shell which has charge distributed over its surface uniformly. Our question is to find field inside it at say certain distance small r from it over here. This is the point where we are supposed to find the field. Now we can see that the charge distribution is having a spherical symmetry. So the field pattern is known. The field pattern would be radially away from the center. So let us assume that this is the field pattern. We are concerned only with the field inside, so we haven't drawn the line outside. We are not concerned with it right now. So this is the point where we are supposed to find the field. Now we can make a guess that every point which is at distance r from the center will have the same strength of field. So if we draw a sphere around it of radius small r, at every point on that surface field will be same. Let's draw that. This is the surface shown by the broken line. So every point on the surface shown by this broken line will have the same electric field. Let us call it E. So E is constant over this surface. And this surface, spherical surface, will act as our Gaussian surface. We'll apply Gauss law to it. So first let us try to find the flux by definition. We'll first need to draw the normal to this surface. So let's draw the normal to the surface. Normal, as this Gaussian surface is a spherical one, normal will be pointing away. So this is the direction of normal. So what do we mark over here? That electric field and the normal, they do have the same direction. Means angle between them theta is 0 at every point. Electric field is constant and theta is 0, that is also constant. Now let's calculate the flux through this surface by definition, that is Es cos theta. This is the formula for flux, Es cos theta. E is not known, this has to be found. Let it be, area is 4 pi square, theta is 0, so cos 0 is 1. So this is flux by definition. Now let us try to find out the charges lying within this Gaussian surface, inside this Gaussian surface. We can very easily see that whatever charges are present, they are present outside this Gaussian surface. There is no charge within this Gaussian surface. So obviously charge inside the Gaussian surface is 0. Write it down. Q inside means charge inside this Gaussian surface is 0. Now let's apply Gauss law to it, to this Gaussian surface. This is Gauss law, which says net flux is net charge inside divided by epsilon naught. We have the value of flux in equation 1 and charge inside in equation 2. So substitute the value of phi and q inside from these two equations. So this is what we get. E into 4 pi square, that is phi, is 0 by epsilon 0. So this obviously means electric field is 0. So field inside this uniform spherical shell is 0. This is our conclusion. Electric field inside the uniformly charged spherical shell is 0. There is no field inside a uniformly charged spherical shell.